Okay, in this video, we're going to be interested in this linear non-homogeneous ODE of second order A, B, and C. Could be constants or actually functions of x. The f of x on the right hand side does not depend on y. So actually the reason why this equation is non-homogeneous is because of that f of x. We have looked at the case where this side is 0 before, and the theory for that in practice is fairly established now. So the process of solving one can be broken into 4 steps, which we're going to put the details to right now. So step 1, the first thing we are going to do is we're going to find what we call the complementary solution of equation 1. Complementary solution. So the complementary solution, we're going to denote YC. How do we find the complementary solution? What we do is we go back to equation 1 and imagine that this term was not there. Okay, so we solve what is called the associated homogeneous ODE. So the equation 1 is non-homogeneous, but there is an associated homogeneous ODE which we can obtain by simply letting f be 0 in equation 1. And so that's going to give us this. We have already mentioned that solving this type of equation we've already dealt with in several of our previous videos. So this is going to be step number 1. Then step number 2 is we look for what is called a particular integral. Okay, so we find the particular integral. Actually the main subject of this video is in this step number 2. So particular integral, which we're going to abbreviate PI. Particular integral, we are going to denote YP. So that is in step number 2. There are 2 methods of finding the particular integral. The one method is what is called the method of undetermined coefficients, which this video is going to be dealing with. There is another method which is called the method of variation of parameters, which we are going to look at, study in a subsequent video after this one. So right now we're just going to focus on this method here. Right, anyway, so then there is going to be step number 3. In step number 3, we write the general solution of equation number 1. Write the general solution, which we are going to denote YG. The general solution is going to be simply the sum of the complementary solution plus the particular integral. All right, since one is a linear equation, then it satisfies what we call the principle of superposition. Principle of superposition says that if YC is an equation, is a solution of the ODE, and YP is a solution of the ODE, then the sum of them is also going to be a solution. So the general solution is going to be given by YC plus YP. Then the final step, which is only going to be applicable if boundary or initial conditions are given, is going to be step 4. So let's call this one equation number 3. So in step number 4, we are going to apply initial or boundary conditions to the general solution if they are given. Okay, so of course, if there are no boundary or initial conditions, then step number 3 is going to be the last step. All right, so now let's focus on the method of undetermined coefficients. So how do you find the particular integral? Okay, so in the method of undetermined coefficients, we determine the particular integral by assuming a solution of a form similar to f of x. Yeah, so we find yp by assuming a function of the same form as f of x. So a function of the same form as f of x, but this function is going to have some undetermined coefficients. So that's where this method gets its name. So how does this work? So let's list some forms of f that may appear. So if f of x, for instance, is a polynomial, then here I'm going to put the form of yp that we are going to use. So suppose f of x is a quadratic term. Then what we're going to do is, for yp, we are going to assume a quadratic of the most general form. So with coefficients a, b, and c. So if our f is just x squared, then we look for yp of the most general form of a quadratic. Similarly, if f is just x, then we are going to assume yp to be ax plus b, where these a, b, and c coefficients are determined by substituting into the ODE. Okay, now if f is some exponential function e to the alpha x, then we let our yp to be ae to the alpha x, where this a is determined by plugging into the ODE. If f of x is sine alpha x or cosine alpha x or both, okay, maybe let me just do this separately. Then we assume yp to be a cosine alpha x plus b sine alpha x. So if f is just alpha, sine or cosine, then we always include both of these. The reason is because when you differentiate each of these, you get the other one. So even if this is just cosine alpha of x, then we assume the same form, cosine alpha x plus b sine alpha x for our yp. Then lastly, if we have something like xe to the alpha x, then this is a product of these two. So what we do is we are going to get the most general polynomial of degree 1 here, then we multiply it by alpha x. All right, so that's the guidelines into how we find the particular solution. Now let's look at some examples, and then we'll take it from there. All right, so we have got some examples here. We're going to start off with example A. So in example A, we have got y prime minus 2xy excuse me, equal to x. We have got an initial condition on x equals to 0, y equals to 1. So as we mentioned, the coefficients of the ODE could be functions of x, like we are having here. So the first thing we're going to do is to write out the associated homogeneous equation, which is simply the equation obtained by setting the right hand side to 0. So here we're just going to have y prime minus 2x, y equal to 0. Now this is a first order linear equation, which the type of which we have already dealt with. If you'd like to have a look at our video on first order linear ODEs, then that would be useful. This is also separable, but we're going to solve it here using the fact that it's linear. The integrating factor is simply going to be e to the minus x squared. Let me put it here, e to the minus x squared, and so multiplying the ODE by this is going to give us ye to the minus x squared prime is equal to 0. Then if we integrate on both sides, then ye to the minus x squared is equal to k1, where k1 is an integrating a constant of integration. So the complementary solution is going to be k1e to the x squared. So that completes step 1. Then in step 2, we have got to find the particular integral. Okay, so we said the particular integral is the form of it is going to be influenced by the form of f. F here is just a linear polynomial. So we're going to assume a linear polynomial of the most general form. So we're going to let yp be a plus bx. We have got a first order derivative in this ODE here. So we need to find the first order derivative of yp. Actually is going to be b. Then we substitute into the ODE. So we have got y prime. So y prime here is b minus 2x times y, which is a plus bx, and then the right hand side is x. If we remove brackets here, then we are going to have b minus 2ax minus 2b x squared. So we've got a polynomial on the left hand side and a polynomial on the right hand side. If the two sides are equal, then the coefficients must be the same. So that's exactly what we're going to do. So we're going to compare the coefficients of the powers of x. Going to compare coefficients of powers of x. So if we start with x squared, on the left hand side, coefficient of x squared is minus 2b. On the right hand side, coefficient of x squared must be 0 because there is no x squared here. So it's like a 0x squared. So this must be equal to 0. So that tells us that b is equal to 0. Then we go to the coefficient of x on the left hand side. Got minus 2a here. On the right hand side is 1. So that tells us that a is negative 1/2. The 1 for x to the power 0 is already sorted because we already found that b is 0 here, not 2. We already found that b is equal to 0, which is in agreement with the terms involving x to the power 0. So our particular solution, therefore, is going to be given by this expression with, so b is 0 and a is negative 1/2. So it's just negative 1/2. Then from this, we can write the general solution. It's going to be yp plus yc. So yc, remember, is k1e to the x squared, and then yp is negative 1/2. Then we are going to apply the initial condition. So remember, when x is 0, y is 1. So on this side, we're going to have 1. And this side, we are going to have e to the power 0 minus 1/2. Then this is going to tell us that k is 1 plus 1/2. It's going to be 3/2. And so our particular solution is going to be 1/2 into 3 times e to the x squared minus 1. All right, so that sorts out our part A. In part B, we have got y double prime plus 5y prime plus 6y is equal to 18x squared. So again, the associated homogeneous equation this time is an equation of order 2. Okay, the auxiliary equation for this one is going to be r squared plus 5r plus 6 equal to 0. This can be factorized into r plus 2 times r plus 3. The solutions of that of this will be -2 and -3. So the complementary solution is k1e to the minus 2x plus k2e to the minus 3x. Then for the particular integral, so we are going to seek particular integral yp. We have a quadratic on the right hand side, so we're going to look for a quadratic of the form a plus bx plus c. So we need to substitute this into the ODE. The ODE has got a first order derivative term and a second order derivative term, so we need to work out the two derivatives for yp. Yp prime is going to be 2ax plus byp double prime is simply going to be 2a. So substituting into the ODE, okay, so we're going to have second order derivative, which is 2a, and then plus 5 times the first order derivative, which is 2ax plus b, and then plus 6 times the yp, which is going to be a squared bx plus c. This is equal to 18x squared. Then if we just sort out the right hand side, starting with the highest powers of x, so that term is going to give us the highest power of x, which is 2 here. Then the terms involving x is going to be 10a here. It's going to be 6b there. Then the constants are going to be 2a from here, 5b from here, and 6c from there. Right, now the right hand side, if we like, we can write it as 18x squared plus 0x plus 0. So what it does mean is that when we do the comparing, Then the coefficients of x squared on the left hand side is 6a, on the right hand side it's 18. So this tells us that a is equal to 3. Coefficients of x on the left hand side, we have got 10a plus 6b, 10a plus 6b. On the right hand side it's 0. So if you plug in a there, that's going to give us b is -5. Then the constants on the left hand side, we've got 2a plus 5b plus 6c. On the right hand side it's 0. Again, if we solve this, we should get c is 19/6. So what this is telling us is that the particular integral is 3x squared, a is 3, b is -5, c is 19/6. So the general solution, which is yc plus yp, so this one is going to be equal to k1e to the -2x plus k2e to the -3x plus 3x squared minus 5x plus 19/6. So that is going to be the solution for part B. All right, we're now going to go to example number C. Example number C, we have got y double prime minus 2y prime minus 8y is equals to 4 times sine 2x. The associated homogeneous equation is y double prime minus 2y prime minus 8y equal to 0. The auxiliary equation of this is r squared minus 2r minus 8 equal to 0. This we can factorize into r minus 4 into r plus 2. So the complementary solution going to be k1e to the 4x plus k2e to the minus 2x. Then for the particular solution, the right hand side is a sine of 2x. So what we're going to do is we're going to look for yp of this form: a cosine 2x plus b sine 2x. So the 2x is from here. We said if this is either sine or cosine, the particular solution must always have both of them here, because these sine and cosine are basically the same function. One is shifted through pi on 2 of the other. Besides, if you differentiate this, you get this. If you differentiate this, you get the other one, or the negative of. So let's do the derivatives. So yp prime is going to be 2 into b cosine 2x minus a sine 2x, and the second order derivative is going to be negative 4 of this one, exactly as it is. B sine 2x. Right, then we can substitute into the ODE. So the ODE becomes, so on the left hand side we've got y double prime minus 2y prime minus 8y. So y double prime, just this one, minus 4 into a cosine 2x plus b sine 2x minus 2 times, there's already another 2 here, so that's going to become a 4. So 4 there, b cosine 2x minus a sine 2x. Then the last one is minus 8 times a cosine 2x plus b sine 2x. This is y, this is y prime, this is y double prime. Then on the right hand side we've got 4 sine 2x. So what we're going to have to do is collect like terms on the left hand side. So if we just take the let's start with the sines. Okay, so for the sines there is one here, one there, and one there. This one is going to be positive because we've got a minus here and a minus here, so that's going to be positive for a. And then these two are both negative. There's minus 4b here, minus 8b there. So it's going to be minus 12b times sine 2x. Then we do the cosines. We've got the a's here, minus 4 and minus 8. So that's going to be minus 12. And then there's this one here is minus 4b. That's going to be, these are the cosines now. Cosine 2b, 2x. Then on the right hand side we've got 4 sine 2x. Then the coefficients must match. So coefficient of sine on the left must be the same as the coefficient of sine on the right. So on the right we've got 4, this side we've got that. So that tells us that 4a minus 12b is equal to 4. And then, of course, minus 12a minus 4b must be equal to 0. This is just a simple linear system. If we solve this, we find that a is 1 over 10 and b is minus 3 over 10. So our yp is 1 over 10 into cosine 2x minus 3 sine 2x. Now, so notice that our solution has got both of these. What this means is that if we had chosen this one to only include this term, then straight away our solution was going to be bound to be wrong. Okay, so therefore the general solution is going to be k1e to the 4x plus k2e to the minus 2x plus 1 over 10 cosine 2x minus 3 sine 2x. All right, so I think we are going to end this video here. So we've just done A, B, and C. We are going to do D in part 2. Thank you for watching.